hard. In our last video and our videos from the previous section, the many of those, and hopefully that's about to pay off with a much quicker now access to some of these problems. For section 2.3, we did the theory for the more general case, nth order, higher order, linear ODEs, right? Now we're going to look at the constant coefficient version of those, right? So linear, we could have variable coefficients in front of our function or their derivatives in the ODE, in the linear ODE. But when we've got variable coefficients, that makes it super hard to find the actual individual sets of solutions that make up the fundamental solution set. We've got all the theory now for what will make up the general solution, but unless we have constant coefficient equations, we are going to have a much harder time, if not no time, finding those solutions, which is really pretty crazy, right? I mean, we can only solve constant. That's just crazy. And that's not true. We can't only solve those. But as far as getting nice little explicit solutions, there's one special type that we've looked at a little bit with non-constant coefficients where we'll get some nice explicit solutions, and other than that, we're going to have infinite series, power series, okay? But that's not what we're doing now. We're talking about our beautiful, nice constant coefficient differential equations. And so let's just do some homework problems. Woohoo! Here we go. 2.3.1, here it is. Y triple prime minus y double prime plus y prime minus y is equal to 0. Okay, solve, right? Find all functions out there in the world. That's what this equation is saying. Find all functions out there in the world whose third derivative minus their second derivative plus their first derivative minus themselves ends up just being 0. What are they? Okay? What are all of them? Well, again, you could guess, but that's just not a very good idea. And so what do? We apply our same idea of, since we have constant coefficients and of derivatives, linear combinations, right, of y and its derivatives, and we understand the exponential function and how its derivatives work, we use this same guess that we did in second order differential equations, that y is e to the rx, right? Y, because y prime, right, what's the derivative of e to the rx? Good, r e to the rx, right? We're good at this now, right? The derivative of this guy ends up being a constant times itself. So it makes sense to think that things like this will be solutions of differential equations that involve constants times derivatives of the function. Y double prime then is good, r squared e to the rx, right? Y triple prime is good, r cubed e to the rx, right? We plug all of that in, right? For each one of those guys, I'm going to be able to factor out an e to the rx. I'm just going to go right there, okay? We get an e to the rx times what? Y triple prime, right? You could probably do this without, right? We should be getting good at this now. Minus y double prime, that was going to be my r squared guy, plus the y prime guy, that's my r. I've already pulled out the e to the rx. Minus my y guy, well, let's multiply that just 1, right? Okay. So if we assume that a solution of the form y equals e to the rx exists, then that turns this differential equation into this algebraic equation. And what do we know about e to the rx? We love this guy is always positive and therefore never 0. So what does that tell us, right? That tells us that we have a characteristic equation, right? A characteristic polynomial now for this ODE, which is an algebraic equation, and it is r cubed minus r squared plus r minus 1 is equal to 0, right? Okay, well now this is a cubic polynomial, right? Oh, look, this was a what order? Third order ODE, right? This guy was third order. Third is higher than second, right? Okay, and what do we get, right? A cubic polynomial, right? Okay, yeah? So we know that there are 3 such roots, right? And our goal is to go after them and find them. Again, by now, this idea, you ought to be thinking, when I look at this constant coefficient ODE, I can immediately write down this characteristic polynomial without having to go through this step. But it's important to know where that step came from as well, right? It's important to be able to do both, right? So r cubed minus r squared plus r to the 1 power minus 1, right? There's a 1 coefficient of y there, right? 1 times r to the 0. This is the 0th derivative, right? Okay, so how do we solve this cubic? Oh no, we gotta factor cubics, right? Okay, well, take it easy here. All right, let's see, what can we do? What do you notice that you you look for something that you can nicely factor in groups and pull out, right? So if you're looking at these 2 guys and these 2 guys, what should I do with that guy? Good, just pull out an r squared from that, right? Then that term becomes r squared times r minus 1, and then what do I have sitting here? Oh, a nice r minus 1, right? And that's equal to 0. And so therefore, what should I do, right? Factor out an r minus 1, right? Because I've got a term of r minus 1 in each one of these terms. So I can factor an r minus 1 out, yeah? And then what do I have left after I factor the r minus 1 out? My r squared right here, yes? And then what? Good. Plus 1 right there. Yeah, right? Okay, and so now we have this written in this beautiful form of a product of 2 things is equal to 0, right? And then if a product is equal to 0, then each part, the only way that's possible is if each part could individually be 0. So what do we get, right? We got r minus 1 is 0, right? That's the outer piece, the outer factor, and that gives us r equals 1 is a root of this cubic polynomial, right? So we've got at least 1 real root, right? Okay, well then what does that then leave? That leaves r squared plus 1 is equal to 0. Okay, does that guy factor? Well, that's a trick question now, isn't it, right? It doesn't factor if we're in the real world, right? In calculus, we would say that doesn't factor, that there's no value of r that makes us 0. But that's not where we are now, right? Okay, so we know from what we did with our complex variable work that this guy, right, r squared plus 8, alpha squared plus beta squared, this guy factors into r plus, good, I and r minus I, right? It does factor to that, yeah? Right? R times r is r squared, plus IR minus IR cancel, and then minus I squared. What is I squared? -1. Minus a -1 is a +1, yeah? Okay, so what does that say that we get out of this quadratic? R is -I, and r is I, right? Set that guy equal to 0 and set that guy equal to 0, yeah? So these guys are complex conjugate roots, right? Complex conjugate roots are equal plus or minus I, yeah? This guy's running out of ink maybe, we'll switch to another one. Now, if you didn't think to do this, right, you could think to do, okay, r squared, ooh, that one's nice, right? R squared is equal to -1, that's another way, right? And then be like, okay, r is plus or minus, don't forget that, that's critically important, the square root of -1. That's just notation. As we talked about, that means r is plus or minus I, right? I, okay? We understand where that guy came from. I. Various ways of thinking about I squared is -1. Okay, but, so here we are, either way, we have our complex conjugate roots, right? And so, when we think of complex conjugate roots, r is equal to alpha plus and minus I beta, right, in general. So for us, what is alpha here? Well, there is no real part to these. These are purely imaginary roots. So alpha is 0 for this problem. And what is beta? What is beta? What is multiplying I? What's multiplying I? Good, 1, right? Beta is 1, yeah? Okay, so this guy gives rise to a solution e to the rx, where r is 1, right? So this guy gives rise to a solution y1, which is e to the 1 times x, right? Which is just e to the x, that's y1, right? This guy gives us two solutions that are real as long as we remember how to deal with this, right? So what was true in the complex conjugate case? We would have a complex valued solution, two complex valued solutions, but we want two legit real valued solutions, and we went through a lot of work to show that we could just, this guy will correspond to one function, we'll call it y2 since we already have a y1 there, that would be e to the alpha x cosine of beta x, right? And then another function, y3 we'll call it, right? Which would be e to the, alpha x sine beta x. Uh-oh, I'm getting texts. Whoops. Okay. All right, so here we go. Back to where we are, right? So what is alpha for our problem? Alpha is 0 and beta is 1, right? So therefore, this gives rise to a solution, right? y2 is equal to e to the 0x, right? Cosine of x, because beta is 1, right? Alpha is 0, I mean the 0x is just 1, right? Cosine x, and then y2 would be, same thing, e to the 0x, I'll just put the 1 in here so that you see it, right? 1 times sine of 1x, right? Well, that guy is 1, and so that's just sine x, right? So those are our, whoops, not y2, y3, right? Yeah? Okay, so here we have our three solutions that we need. So therefore, based on what we did last time, provided what? What has to be true about these three different solutions? We have three solutions to a third order equation. What has to be true? Provided e to the x, cosine x, and sine x are what? I heard it. Linearly independent when they form a fundamental solution set for our ODE by our theory from last time, right? And that would then say then the general solution to this ODE is, you guys tell me, y is what? A linear combination of those three solutions, right? Okay, we're still going to go back and talk about this, right? But provided they are, then the general solution is linear combination, so C1 times Y1, which is e to the x, plus C2 times Y2, which is cosine x, plus C3 times Y3, which is sine x. And there is all possible functions out there in the world that satisfy this restriction on their derivatives, right? Differential equation. So let's justify this, okay? Because we need that to be true, okay? Let's justify that e to the x, cosine x, sine x are linearly independent. So what do we do when we do that, right? Oh, we talked about the Wronskian last time, but this would be a 3x3 determinant, and it would be more work than needed, and you know, some of you don't even know what that even means, so we're just gonna talk about what do we want to consider, right? We're gonna consider, right, the linear combination C1 e to the x plus C2 cosine x plus C3 sine x set equal to what? Good. 0, right? For what? For all x real, right? Minus infinity to infinity. What's really nice about these guys that popped up? Where does sine x exist in continuous and differentiable? Minus infinity to infinity. Same for cosine x. Same for e to the x, right? Right? Okay. So that's super nice. So we want this guy to be true for all of those values. And our goal is to show, so is it true that C1 equals C2 equals C3 equals 0 is the only solution to the above equation? Okay, is that true? If so, then they're linearly independent by the definition of linear independence, right? If so, they're linearly independent on all of our. Okay, well, what would we do then? Okay, there's lots of different things to do, right? And your book shows you a variety of different ways to finagle the equations. One thing you can always do is evaluate at various x, because this has to hold for all x's, right? There are lots and lots of different ways to do this, and I'm not even going to show you some of those ways just because, we don't have time to keep talking about lots of other things. All right, so what if x is 0, right? If x is 0, then what does this equation become? C1 e to the 0, so e to the 0 is 1, so C1 plus C2 cosine of 0, what is cosine of 0? 1, good, so plus C2 times 1, plus C3 times sine of 0, what is sine of 0? Good, 0, so that's gone, right? So if x is 0, that equation becomes C1 plus C2 is 0, okay? All right, now let's pick some other nice value. How about x equals, say, what do you think? What's a nice easy value to evaluate this? Good, I heard it. Pi over 2, right? Yeah, right? So if x is pi over 2, then this will be C1 e to the pi over 2, right? Plus C2 cosine of pi over 2. What is cosine of pi over 2? 0, right? And plus C3 times sine of pi over 2. What is the sine of pi over 2? 1. Beautiful. So there we are, a second equation. Yeah? It's 3 equations. We want a third equation, 3 unknowns, so we want a third equation. What's another nice place to evaluate this equation? Lots of possibilities, Let's go with pi. X is pi. Okay, if x is pi, then the equation becomes C1 e to the pi plus C2 cosine of pi. What's cosine of pi? Cosine of pi? -1, right? Minus C2, yeah? What is sine of pi? Good. Sine of pi? 0. Good. So here, like, the whole point was to make our equations a lot simpler, right? So now, let's see if we can come up with a nice systematic way of dealing with this. So this equation says C1 is equal to negative C2. So it would be nice if we had like a really nice systematic way of dealing with multiple equations, right? And equations and unknowns to solve for the unknowns. That would be really nice, right? Okay, anyway, you might see that at some point, or maybe you already have. So C1 is negative C2. That's what that equation says, right? Okay, well let's put that in right down here, okay? Okay, well that would then say, right, that C1 times e to the pi, well minus C2 is C1, so I'm just going to do that, right? Okay, would be plus C1, right? Would equal 0, yeah? And then I could factor out the C1, yeah? So C1 e to the pi plus 1 is equal to 0, yeah? Okay, does that make sense? Well, this is a product of 2 things, right? It seems to keep coming up all the time. Is e to the pi plus 1 0? No. And so therefore, what? C1 must be 0, right? And if C1 must be 0, well then, C2 must be 0. And if C2 must be 0, well, we're looking back here because now we need to go here. We don't care about C2, but we do care about is in this equation, right? If C1 is 0, then C3 is also 0, right? So that's a lot of arrows pointing everywhere, but whatever it is that you do, make sure I can follow it so that you're justifying that what is true. If that equation holds, C1, C2, C3 is the only solution, check. Therefore, they are linearly independent. Therefore, they form a fundamental solution set, and this is the general solution, period, based on our theory, right? Awesome. We are not leaving out any possible solutions with this solution, yeah? Because if we assign initial conditions, which, you know, have fun, we would need 3 of them, right? One on y, one on y prime, and one on y double prime, and then you would need to take this derivative, so then you wouldn't have a set 3 equations for the 3 unknowns, C1, C2, and C3, but they would be guaranteed to be solvable, right? For any arbitrary initial conditions. And so, we again see a need for some nice systematic way of solving systems of equations, of algebraic equations, and equations in n unknowns. All right, let's do another example. Sound good? Okay, let's look at number 2. We're just doing homework problems here, okay? What does this mean? Does that mean y to the 4th? No, good. The 4th derivative of y, right? Minus 5 times y triple prime plus 6y double prime is equal to 0, okay? Alrighty. What's the characteristic equation for this constant coefficient? What order? 4th order, right? ODE with constant coefficients, right? Okay, so what's the characteristic equation? What are we going to get out of this guy? Good. Oops, r to the 4th, yeah? Right? Minus 5r cubed, very nice, plus, good, 6r squared, we're done, equals 0, right? Okay, we're pros at this now, yeah? Okay, how do I solve this? Good, I've got a r squared in each term. Let's factor that guy out. What do I have? R squared minus 5r plus 6 is equal to 0 then, yeah? Does this factor more? It does, so don't forget that guy. He comes along for the ride, and then this factors more, right? So it factors into what? R and R. Be careful. 6, 1, 3, 2. Right. This is a minus, this is a plus, right? These guys have to both be minuses, right? And so it can't be 6 and 1, right? It's got to be 3 and 2. Yeah? Okay. All right, so what do we have? Nice factored form of our characteristic polynomial. Set equal to 0 makes it super easy to find the roots, right? How many roots are there? It's a 4th order polynomial, there's 4 roots, right? So this guy says 1 root is r equals 2. This guy says 1 root is r equals 3, right? This guy says what? Good. R equals 0 is a double root. Oh, we saw that before, right? With quadratics, right? Double roots, okay? When we were back in section 2.2, right? What else do we call this? A root of multiplicity, what? Multiplicity 2, right? Root of multiplicity 2. Okay, so what does that mean? That means we're going to get 2 solutions out of this guy. We're going to get a y1 and a y2, right? And then this guy's going to give us a y3, and this guy's going to give us a y4, right? Okay, well, let's just write down what y3 is first. What's y3? If I just label it this way, it doesn't matter. y3 would be e to the 3x. Now, that 3 and that 3 have nothing to do with each other, right? Okay, good. What is y4? E to the 2x, right? The root is 2, okay? And then these guys are going to give me my y1 and my y2, right? Well, what is y1? y1 is e to the 0x. We've already seen this, right? And what is e to the 0x? 1. Good. And then what is y2, right? It's the second solution associated with the root r equals 0, right? The reduction of order method, which we went through with repeated roots, says, what do? Yeah, multiply x times this guy, right? So x times 1 is x. So there's my 4 solutions, right? So provided 1x, e to the 2x, and e to the 3x are what? Yep, linearly independent, right? Provided this is linearly independent, then our general solution is what? Y equals C1 times 1, right? Plus C2 times x, plus C3, uh-oh, I wrote them, I'll just keep it in this order. C3 e to the 3x, it doesn't matter, right? Okay, it doesn't matter what order they're in because it's arbitrary constants, yeah? Plus C4 times e to the 2x, yes? Okay, so that is just the same as y is equal to C1 plus C2x plus C3 e to the 3x plus C4 e to the 2x, right? An arbitrary constant, a different arbitrary constant times x, plus a different arbitrary constant times e to the 3x, plus a different arbitrary constant times e to the 2x. This is our general solution. I'll leave it to you to show that indeed that is true. You hopefully are beginning to get the hang of how this all works when we're starting to get these different types of things that show up in solutions of differential equations. We already know these two guys are separately themselves linearly independent. We know these two guys are linearly independent. That came out of other things that we were doing. The 4 of them as a single set are also linearly independent, okay? So let's do another example, right? Okay. Oh, before we do that, let's mention this one thing here. This little piece we kind of already knew. Now, remember, where did that come from? That came from this r equals 0 double root, right? Okay? But if you look back up here at the equation, right, there is no y prime, there's no y, right? So this is a linear function. We take 2 derivatives of this guy and he's gone, right? Okay? And so, therefore, right, any linear function is going to satisfy this differential equation because you're just going to get 0 minus 5 times 0 plus 6 times 0 is 0, yeah? Okay? So that's the arisal of that, you know, the genesis of that piece of the solution. Does that make sense? Then you can kind of see that was coming from the equation, yeah? Okay? Now, if there was a y in there, then that would be not the case anymore, right? Okay. Let's do another problem. Now let's turn this around a little bit, okay? So we're getting pretty good at this. Now let's turn it around. So let's recall that last time we showed that e to the x e to the x, and x squared e to the x are linearly independent on R. Pretty much everything is going to be for us on R, minus the infinity. Okay, just saving myself some space in writing. All right, we showed that those are linearly independent. Okay, well, here's a new question. Let's turn this around, right? If these are linearly independent functions, well, do they solve a particular differential equation? Can you give me a differential equation they would solve, that they would be a fundamental solution set for, okay? So let's find an ODE that has e to the x, x e to the x, and x squared e to the x as a fundamental solution set. Okay? So now we start with solutions and we want to create the differential equation. All right. Well, so our knowledge here ought to be kicking in. What had to be a root of the characteristic polynomial? First of all, there's three functions there. So what degree is the characteristic polynomial? Good. Third order, right? Okay, what had to be a root? Well, if this guy is a solution, right? R equals 1 must be a root. Yeah? Of the characteristic polynomial. Yeah? Okay. This is very similar to what we saw over here, right? Okay, now how do we get x e to the x and x squared e to the x then? Where's that coming from? Well, it's not complex, right? It's not coming from the complex stuff, right? Because you don't have to cosine of beta x and sine beta x, right? So what do we got here? Like this is a second solution associated with the root r equals 1, right? Because remember, if this guy is like our y1, then what did we do? The reduction of order method, right? When we found another solution, reduction of order said look for y2 as v of x times y1 of x, right? And then we went through all the calculations and it turned out that v of x, the easiest v of x was just x, right? And so that our second solution here, y2, is x times y1. So that's telling us that we've got a second solution associated with a root, r equals 1, so that root had to be at least a double root, right? Root of multiplicity 2 at least. And now let's look at this guy, y3. Well, what is y3? y3 is x times y2, right? X times x e to the x, right? That's x squared e to the x, yeah? Okay? Right? And so what actually happened, right, to get y3? Same idea of the reduction of order method where v of x ends up also being x again, right? And so what does that mean? We created another solution from a previous solution. So this is a second solution associated with that guy, which is a third solution associated with that guy, which tells you what about the root, okay? So this is our third solution associated with the root r equals 1. So what do we know about that characteristic polynomial then? Good. That characteristic polynomial must have been r minus 1 quantity cubed is 0, right? We must have reduced down to that, yeah? So that r equal 1 is a triple root, right? Is a root of multiplicity 3. Triple root, right? Okay, well then if that's the case, right, that's how we would generate those three solutions. It's just the same idea of reduction of order reapplied, right? Okay. So now we would have to expand this out to figure out what the differential equation was, right? So r minus, if you don't remember the cubic formula, it's not so hard. You just do it yourself, right? R minus 1 times r minus 1 quantity squared would have to be 0, right? That's what r minus 1 cubed is, yeah? Okay, well that's the same as r minus 1 times, what is this thing squared? Yep, r squared minus 2r plus 1, right? Yeah? FOIL. Okay, and now it's just one more step. What are we going to do? We got to distribute this guy across all of this, and then this guy across all of this with the minus, right? It's just distributive law, right? So we're going to get an r cubed. Whoops, r cubed. R times r squared is r cubed. Yeah. Then we're going to get a minus 1 times r squared and a minus 2r squared. Minus r squared minus 2r squared is minus, good, 3r squareds. Yes? Then what about the linear terms in r, right? We've got a plus 1r, and then we've got a minus times a minus is a plus 2r. Plus 1r plus 2r is plus 3r, right? And then minus 1 times plus 1 is minus 1. Yeah? Okay, is equal to 0. This is our characteristic equation. Therefore, an ODE, right, you could always multiply everything by a constant, right? An ODE would be what? What would be the ODE that would correspond to this characteristic equation, just explicitly? Third in r cubed, right, is going to correspond to a third derivative, right, of y. So y triple prime, right, minus, good, right, and r squared, right, is going to correspond to the second derivative. So minus 3y double prime, right, plus 3y prime, r to the first power, 1 derivative of y, right, minus 1, is that right? Is 1 right? No, good, that wouldn't be homogeneous, right? These are all homogeneous too, right? Okay, homogeneous. Yeah, still doing homogeneous. So what is this guy? Good, minus 1, right? This is r to the 0 power, that's the 0th derivative, right, of y. And so here we have an ODE that would have those 3 guys as a fundamental solution set. So we know from what we just did that the general solution of this ODE is what? And there's our guys. Y is equal to C1 e to the, whoops, sorry, let me just erase that so I have more space. There's our 3 solutions, our fundamental solution set. So y would be C1 e to the x plus C2 x e to the x plus C3 x squared e to the x, right? C1 y1 plus C2 y2 plus C3 y3. Yeah? Right? Okay. Another way to write that, which can often lead students astray, so I generally say just write it like this, okay? But another way to write it is to factor out that e to the x there, right? And write it as C1 plus C2x plus C3x squared e to the x, which is equivalent for sure, but it clouds the issue that this is C1y1 plus C2y2 plus C3y3, right? And then you start getting confused later. So anyway, just something to pay attention to, okay? Both equivalent solutions, but where did this come from? It came from C1y1 plus C2y2 plus C3y3. Yep? Alrighty. How about maybe one more problem and call it a day? Does that sound good? Does that sound like fun? Right? Woo, this could be the shortest video we've had in a long time. We'll see. I should just quit talking and start doing problems so that we can the characteristic equation for an ODE could be factored to r to the 5th times r minus 4 cubed times r squared plus 4 quantity squared is equal to 0. Okay? Now we're doing something even more different, right? Okay? We started with differential equations, go to characteristic equation, find the fundamental solutions, right? So you can write the general solution. Then we took a twist on that, like here's some functions, they're linearly independent. Give me an ODE that there are fundamental solutions set for, right? And so we had to come up with the characteristic equation based off of what the solutions looked like, right? So, and then from there, we got the differential equation. So what in the world are we being asked to do with this problem now? Well, we certainly don't want to be expanding that out, so let's hope they don't ask for the differential equation, right? They being me. Okay, so anyway, what's our first question? What order ODE is this? What order ODE, not is this? This is not an ODE, right? What order ODE has this characteristic equation? So what is the order of the differential equation that has this as a characteristic equation? What do you think? I think I'm getting it. I think I'm getting it. Well, it's the same as what is the degree of this polynomial, right? So what is the degree of this polynomial? Well, I got 5 right here. We got 3, so that's 8. Yeah, and this one, be careful, right? 4th order, so 8th plus 4th is 12th. This is a 12th order, this would correspond to a 12th order ODE, right? That means how many solutions do we need that are linearly independent? 12, very good, okay? Okay. I'll let you start cruising on that. I'll write the next question. The next question is, what is the general solution to the ODE? Well, that's pretty awesome. We're going to write down the general solution and not even write down the ODE, right? That's way better, right? Writing down the ODE would be ugly and messy, yeah? Okay. Hopefully you see why. All right, what's the general solution to the ODE? Well, what do? Right? We've got to look at our roots, right? So what do we have here? R to the 5th. What does that mean? What is a root? Good. R equals 0 is a root of multiplicity what? 5, right? It's a root of multiplicity 5. So what am I going to get out of this guy? 5 solutions. Y1, Y2, Y3, Y4, and Y5, right? Okay? What is Y1? E to the 0 times X. We should be getting good at this now, right? Which is just 1. So what is Y2? Right? X times this guy, which is X, right? What is Y3? Same idea that we just talked about before. Reduction of order, look for a function v of x times y2, v of x times x. You do the exact same process, you get that v of x equal x, gives us the simplest solution. So x times x, x squared. So what do you think y4 is going to be? Good, x cubed, and y5, good, x to the 4th, right? Kind of what we said earlier with the other problem, when we add them all together as a linear combination, will be a 4th order polynomial, and based on what we're kind of seeing in here, that we must have not had derivatives of, we must not have y, y prime, y double prime, y triple prime, the fourth derivative, so that we could have a solution that ended up just being annihilated. It's actually related to the idea of the method, being annihilated by the differential equation, okay? So that's our 5 solutions coming out of there, right? Okay. Then what else? Well, then we're going to have what? R equals 4 is a root of multiplicity 3, right? So R equals 4 corresponds to a solution that looks like what? So I'm going to get, for this guy, I'm going to get 3 more solutions, y6, y7, and y8. Yeah? So y6 is going to be what? Good. E to the 4x, e to the rx, right? That's where they're coming from, yeah? R equals 4. And then what is y7 going to be? Yeah? X, e to the 4x, because of the repeated root case, right? So spending all that time in the quadratics, it really paid off for us now. What is y8? Good. X times y7. So x squared e to the 4x. Yes? Okay. So now we've got the 3 that come out of there. And so then lastly, right? So we'll just come over here. Lastly, we've got r squared plus 4, right? Quantity squared is 0, right? So we know that whatever comes out of here is going to be a double root, right? Double root, yeah? So r squared plus 4 equals 0. You've got 2 things you could do, right? Okay, that either factors to r plus 2i, r minus 2i, or you can think of it as r squared is negative 4, so r is plus or minus the square root of negative 4, which is plus or minus the square root of 4 times the square root of negative 1, which is plus or minus 2i, right? Which we also get from the factoring. So r is negative 2i and r is plus 2i, right? Okay, either way. Regardless, what do we know? These are complex conjugate roots. Once again, they're purely imaginary, right? And so the alpha is again 0, right? And that's nice when the alpha is 0, because then you don't have the e to the alpha x piece multiplying. You just have the beta part, and beta here is 2, right? So because of that, we're already y8, so we're going to get a y9, which is just e to the alpha x, which is e to the 0x, so 1 times cosine beta x, so cosine 2x, right? And then we're going to get a y10, which is the other real valued solution that comes out of just this guy itself, which is, good, sine 2x, right? But this is double root, right? So what are our last 2 solutions, right, that we need? Y11 and Y12. Yep, I heard it, right? Repeated roots, right? So we need a second solution associated with Y9. What's it going to be? X cosine 2x. Same thing, right? You're multiplying the previous solution by v of x. V of x turns out to be x, right? What's the second solution associated with y10? X sine 2x. Yeah? Whew, that's a lot, right? It's a lot of solutions. And so therefore, so it's super important, right, to pay attention to the multiplicity of the root. Let's write down our final solution. What is the general solution of the ODE that has this quadratic, or has this characteristic equation that can be factored into this form, right? The general solution, now, provided all of these functions are linearly independent as one big group in V, they are, okay? Polynomials, exponentials, cosines, and sines. What do we love about those things? Continuous everywhere, differentiable everywhere, right? Life is good with them. The beauty of constant coefficient ODEs. So what do we got? Y is what? C1 times Y1, which is 1, right? So I'll just write C1 plus C2 Y2, so C2X plus C3 Y3, so C3X squared plus C4X cubed plus C5 X to the fourth, right? Now I know I'm done with my solutions corresponding to R equals 0, right? Because I need 5 of those guys. And again, you see you've got a quartic polynomial, right? And let's note, this is kind of important for later, polynomials are generated by roots of 0 for the characteristic equation. That's going to be important to remember very soon, okay? And you see why, right? From how we generated those y1 through y5, right? So it's a polynomial, right, of degree 1 less than the multiplicity of the root, right? 1 less than the multiplicity of the root. Degree 1 less than, right? Multiplicity of that root was 5 because we've got our constant term. All right, so that's part of our solution. Then we got C6, all right? E to the 4x plus C7, x e to the 4x plus C8, x squared e to the 4x. These three guys are solutions corresponding to the R equals 4 root, right? Yeah. And now we want to have space, right? So I'm going to erase this piece. Hopefully you have that. You can always just stop the video, right? And now we need the rest, right? So plus what? All of these guys, right? C9 cosine 2x plus C10 sine 2x plus C11 x cosine 2x plus C12 x sine 2x, right? And these guys are solutions corresponding to our root of plus and minus 2I, right? And because we had a multiplicity. Yeah? So the way you might see this written in your book is probably, again, factoring out the e to the 4x piece and leaving the C6 plus C7x plus C8x squared in a parenthesis. Again, remember where it's coming from, right? Make sure you know where things are coming from. And then similarly, you could group these two guys together and even put them back to back, right? It doesn't matter whether C10 goes with this one, C11, it doesn't matter, right? But then you could factor out the cosine 2x and write it as, you know, C9 plus C10 or 11, whichever it is, times x, and a parenthesis times that guy. But again, remember where it's coming from and why, right? And then that would, then you would put these two guys together as well. That's the way you'll see them written in the text, but I would suggest making sure you write it out this way first, so you make sure you know precisely why the general solution is what it is, why what you are doing is putting together a linear combination of the 12 solutions that go along with this 12th order ODE, and since they are linearly independent, we are guaranteed that all solutions are contained in that awesome expression. That's it. See you soon.